Assalamualaikum and a very pleasant day to everyone. Faida. Thank you for making time to watch our presentation video. So today we will be presenting our topic on Earthworks and focusing on two major construction projects in Malaysia, namely Tun Razak Exchange aka TRX and Merdeka 118. So let's begin with our first case study, which is Tun Razak Exchange or TRX. TRX is one of the largest mixed building use developments in Malaysia and is recognized as the country's first international financial district. This project demonstrates how proper earthwork planning is essential when constructing large developments in highly congested urban areas. TRX is Malaysia's first international financial district located in Kuala Lumpur. It is a 17-acre mixed-use development consisting of offices, residential buildings, hotels, and retail spaces. Because the project required several underground design levels, extensive earthwork were needed. Since the site is surrounded by roads, MRT lines, and existing buildings, careful planning and geotechnical investigation were essential to ensure safe excavation. Next are the parties involved in the project, as you can see the table here. So the successful delivery of the TRX Exchange project relied on the effective collaboration of various stakeholders, including the client, developers, consultants, contractors, and design professionals. These parties had different responsibilities for the planning, design, management, and implementation of the project, and ensured that the project was delivered to the required standard of quality, safety, cost, and schedule. Their collective wisdom and coordinated efforts helped to pave the way to the successful development of TRX Exchange as Malaysia's leading international financial and commercial center. Now, let's move on to the design consideration. The first consideration was the nature and depth of excavation because multiple basement levels required deep excavation while maintaining soil stability. Secondly, urban site constraint. Since the project was in a busy city centre, space for machinery, material storage, and transportation was very limited. Third, engineers conducted detailed geotechnical investigation to understand the soil and rock condition before excavation. Another important factor was groundwater control. Dewatering systems were installed to prevent flooding, soil instability, and excessive settlement. In addition, second pile walls were used as the earth retaining system to support the excavation and minimize ground movement. Finally, because the site was located near an RT station and existing buildings, continuous monitoring was carried out to protect surrounding infrastructure throughout the construction. Next, I will continue to explain the construction methods. The first step was site preparation, including site clearance, utility division, and survey. This created a safe working environment before excavation started. After that, bulk excavation was carried out using hydraulic excavators and dump trucks to remove large quantities of soil and weathered rock. Then, standby walls were constructed around the excavation area to provide temporary earth support and control groundwater movement. Ground improvement was also performed using cement grouting, where the grout was injected into weak limestone zones to strengthen the ground. Excavation was carried out layer by layer through the stage deep excavation, which reduced the lateral earth pressure and improved the excavation safety. Next, I will continue to explain the construction methods. The first step was site preparation, including site clearance, utility division, and survey. This created a safe working environment before excavation started. After that, bulk excavation was carried out using hydraulic excavators and dump trucks to remove large quantities of soil and weathered rock. Then, standby walls were constructed around the excavation area to provide temporary earth support and control groundwater movement. Ground improvement was also performed using cement grouting, where the grout was injected into weak limestone zones to strengthen the ground. Excavation was carried out layer by layer through the stage deep excavation, which reduced the lateral earth pressure and improved the excavation safety.
Assalamualaikum, my name is Sarah, and now I will present about material used for Earthwork project at Tun Razak Exchange, or known as TRX. Earthwork at TRX requires suitable materials to support deep excavation works and to ensure ground stability throughout the construction process. The selection of materials focused on safety, efficiency, and sustainable construction practice. The main earthwork materials used in this project are used excavated soil, engineered fill, granular materials such as sand and gravel, geotextile, and drainage aggregates. These materials play an important role in construction. They help to improve ground stability, support deep excavation works, provide proper drainage and permeability, and also ensure a safe construction environment. Next, I will present the equipment and machinery used in the earthwork project at TRX. The earthwork at TRX is carried out using a coordinate system of heavy machinery to ensure efficient excavation, material transportation, and compaction works. The equipment is selected based on deep basement construction requirements and the need for safety in an urban environment. The first equipment is hydraulic excavators, which are used for digging, loading, and bulk excavation works. They work together with dump trucks in a continuous cycle to improve productivity on site. Next, bulldozers are used for site clearing, soil pushing, and rough grading during cut and fill operations. In addition, scrapers are used to cut, load, haul, and dump soil in a single operation to improve efficiency. For transportation, dump trucks are used to move excavated soil and fill materials between different areas of the site to ensuring continuous material flow. Besides that, mini excavators and loaders are used for trenching and utility works, especially in confined area where precise excavation is required. For deep excavation support, sheet piles, hydraulic trucks, and bracing systems are installed to retain soil and ensure excavation stability. Finally, roller compactors are used for compact fill materials to the required density, which help to prevent settlement and improve ground stability.
My name is Nuhani Sutia binti Sobri. Today I will present about testing. Before excavation start, a geotechnical site investigation was carried out using borehole, standard penetration test, and soil and ground sampling. This helped engineer understand the ground condition and choose the most suitable excavation and foundation method. Next is groundwater was continuously monitored using piezometers and observation well. This ensure the dewatering system work effectively and reduce the risk of ground movement that could affect nearby building. In addition, instruments such as inclinometer and settlement markers were used to monitor wall movement and ground settlement. If any abnormal movement was detected, engineer could immediately take corrective action. Quality cost testing was also performed through some tests, concrete compression, and pipe integrity tests to ensure the concrete and foundation meet the required standard. Overall, the testing program improves construction safety, reduce risk, and ensure the project meet engineer requirement. Moving on the effectiveness of the construction method, the first method was the diagram wall, which act as both a temporary retaining structure and a permanent basement wall. This improves stability and reduce construction time. The second method was stage deep excavation, where excavation was carried out step by step. This reduced the risk of ground collapse and allowed engineer to monitor ground condition throughout the construction process. TRX also use a groundwater control system to keep the excavation area dry and stable, while a geotechnical monitoring system provide real-time data so engineer could quickly respond to any issue. Finally, costs involved. The major costs include deep excavation and earthwork, retaining structures such as the diagram wall, groundwater control system, and continuous monitoring and quality assurance. Although this method require high initial investment, they reduce construction risk, prevent costly repair, and ensure the long-term stability and success of the TRX project.
Assalamualaikum, my name is Anishuhada binti Muhammad Roslan. For this section, I will explain the problem encountered during the earthwork of the Tun Razak Exchange project. The first problem is deep excavation in a congested urban area. The TRX project required deep excavation to construct several basement levels before the main building could be built. Since the project was located in the center of the Kuala Lumpur, the construction site was surrounded by the existing buildings, busy roads, and underground utilities. This limited the working space for the excavation activities and made it difficult for heavy machinery to operate efficiently. Therefore, the excavation work had to be carefully planned and minimize ground movement and avoid affecting the surrounding infrastructure. For the second problem is compact karst limestone formation. The site contained irregular limestone pinnacles and underground cavities, making the subsurface condition highly unpredictable. This increased the difficulty of the excavation because the depth and strength of the rock varied across the site. If these conditions were not properly identified, they could lead to the excavation failure, ground collapse, or additional construction costs. Therefore, continuous geological assessment was essential throughout the earthwork progress. The third problem is high groundwater level. Since the excavation was carried out below the natural groundwater table, groundwater continuously entered the excavation area. This reduced the strength of the surrounding soil and increased the risk of flooding, soil instability, and unsafe working conditions. As a result, groundwater control became one of the most important aspects of the earthwork process to ensure that excavation could continue safely. For the final problem is ground settlement affecting adjacent structures. Deep excavation changed the stress distribution of the surrounding soil, which could cause settlement around nearby buildings, roads, and underground utilities. Excessive settlement might result in structural cracks or damage to public infrastructure. Therefore, continuous monitoring was necessary to ensure that any ground movement remained within the safe engineering limits throughout the project. To overcome these problems, several engineering solutions were implemented during the earthwork stage. The first solution is comprehensive geotechnical investigation. Engineers carry out borehole drilling, soil testing, and geological assessment before excavation begins to understand the subsurface conditions. The information collected help engineers select suitable excavation method and foundation design while reducing the risk of unexpected ground conditions during the construction. The second solution is the installation of diaphragm wall and dewatering system. The diaphragm wall acts as a retaining structure to support the excavation and minimize soil movement, while the dewatering system controls groundwater infiltration by lowering the groundwater level. Together, the system improve excavation stability and provide a safer working environment. Another important solution is the use of the instrumentation and monitoring system. Instruments such as inclinometers, piezometers, and settlement markers were installed around the excavation site to monitor ground movement, groundwater pressure, and wall displacement. This allows engineers to identify potential problems at an early stage and take immediate corrective actions before they become more serious. In addition, the contractor implemented proper construction planning and site management. Excavation was carried out in stage to improve stability, while just-in-time material delivery reduced congestion within the construction site. Proper traffic management also ensure that the movement of construction vehicles cause minimal disruption to the surrounding public roads. Based on this case study, several improvements can be recommended for future earthwork projects. Firstly, building information modeling, which is BIM, should be used more extensively because it improves project planning and coordination before construction begins. Secondly, a smart geotechnical monitoring system should be implemented to provide real-time monitoring and early warning of ground movement. Thirdly, advanced geological investigation together with the 3D ground modeling can provide a more accurate understanding of subsurface conditions, especially in the limestone areas. Finally, sustainable earthwork practice such as reusing excavated material and reducing construction waste should be encouraged to minimize environmental impacts and improve overall project sustainability.
Now, let's move to our second case study, Merdeka 118. Standing at 678.9 meters, it is the tallest building in Southeast Asia. Due to its height and deep basement construction, advanced earthworks techniques were required to ensure excavation safety while protecting nearby heritage buildings and MRT infrastructure. As you can see in the slide, the table shows the parties involved in the project. The Merdeka 118 project's successful completion would not have been possible without the cooperation of different stakeholders, including the client, developer, consultant, architects, engineer, and contractors. During the planning, design, and construction stages, each party brought its specialized knowledge and expertise to bear, delivering the project to its objective in terms of quality, safety, cost, and time. The synergy between their efforts played a crucial role in the successful execution of Merdeka 118, one of the world's tallest and most iconic skyscrapers, showcasing Malaysia's engineering powers and dedication to sustainable urban development. The design consideration for Merdeka 118 were slightly different because of the tower's exceptional height. First, deep excavation was required to construct 5 basement level and support the massive foundation system. Secondly, detailed geotechnical investigation were necessary to understand the Kenny Hill Formation and Kuala Lumpur limestone. Third, groundwater had to be carefully controlled to prevent seepage, uplift pressure, and settlement. Engineers also paid special attention to protecting nearby heritage buildings and MRT infrastructure from vibration and ground movement. Finally, because of limited construction space in the city centre, careful planning of equipment movement and construction sequencing was essential. Now, let's move on to the construction method used for the Merdeka 118 project. The construction started with site preparation, including site clearance, utility division, and surveying to ensure the safe working area. Next, a covered-can retaining wall was constructed to support the deep excavation. Ground improvement using cement grouting was then carried out to strengthen the weak limestone and reduce groundwater inflow. The excavation was completed in stages to improve stability and allow continuous monitoring throughout the excavation process. Next, groundwater control was carried out using dewatering system and monitoring wells to prevent flooding settlements. After that, large diameter board piles were installed to support the heavy load of the super tower with minimal vibration. Throughout the construction, geotechnical monitoring was conducted to detect any ground movement. Finally, backfilling and compaction were completed to strengthen the soil and provide stable support for the completed structure. Overall, this method ensured the safe and successful construction of Merdeka 118.
As one of the world's tallest building, Merdeka 118 requires a highly engineered construction materials to support its deep foundation system and ensure structural stability. The selection of materials is based on project deep excavation works, groundwater conditions, deformation control, and the ability to carry very high structural loads. The main materials used are high-strength reinforced concrete, high-performance concrete, bentonite slurry, steel reinforcement bars, and engineered backfill. High-strength reinforced concrete is used for diaphragm wall, rough foundation, and core structure. High-performance concrete provide high strength and help reduce thermal cracking. Besides that, bentonite slurry stabilize trench wall during diaphragm wall excavation, while steel reinforcement bars improve the strength of the foundation. Lastly, engineered backfill helps minimize settlement and maintain ground stability. These materials ensure the strength, durability, and stability of the Merdeka 118 structure. Next, I will present the equipment and machinery used in the construction of Merdeka 118. Due to its deep foundation and urban location, specialized equipment is required to ensure safe and efficient construction. The main equipment includes diaphragm wall machinery, bore piling rigs, excavators, tower cranes, temporary strutting system, and foundation testing equipment, diagonal wall machinery, and bore piling rigs are used to construct the deep foundation, while excavators and crane handle excavation and material lifting. Tower crane transport construction materials to higher level of the building. Temporary strutting system provides support during the excavation, and foundation testing equipment is used to verify the load-bearing capacity of the pile. Overall, this equipment and machinery help ensure precision, safety, and stability throughout the construction of Merdeka 118.
Now I will explain about testing. Before construction began, a detailed geotechnical investigation was carried out through borehole drilling, standard penetration test, and laboratory tests. This helped engineers understand the ground condition and design a suitable foundation for the super tall building. Next, pile integrity tests and load tests were conducted to ensure the board pile could safely support the building load. During construction, instruments such as inclinometer, piezometer, and settlement marker were also used to monitor ground movement and protect nearby building. In addition, concrete quality was checked through slump tests and compressive strength tests to ensure it met the required standard. Moving on to the effectiveness of the construction method, one of the key methods was the circular confidence retaining system, which provide excellent excavation stability and reduce ground movement around the site. The project also used large diameter board pile to transfer the heavy building load safely to the limestone bedrock, ensuring long-term structural stability. Besides, high-performance concrete was used to achieve greater strength and durability, while building information modeling or BIM, together with real-time monitoring, improved the project coordination, quality control, and also construction efficiency. Finally, costs involved. The major costs include the deep board pile foundation, the circular confidence retaining system, high-performance concrete, and digital technologies such as BIM and monitoring system. Although this method require a high investment, they improve safety, reduce construction risk, and ensure the successful completion of the Merdeka 118 project.
Next, we will move to the second case study, which is the Merdeka 118 project. I will explain the problem encountered during the earthwork stage first. For the first problem is deep excavation in highly constrained urban environment. Similar to TRX, the project required deep excavation to construct several basement levels before the superstructure could be built. However, the site was located in the center of Kuala Lumpur and surrounded by existing buildings, road, and public infrastructure. This creates limited working space for heavy machinery, material storage, and excavated soil. Therefore, the excavation process required careful planning to ensure that construction activities could be carried out safely without causing major disruption to the surrounding area. For the second problem is groundwater infiltration during the deep basement excavation. Since the excavation extends below the natural groundwater table, groundwater continuously enter the excavation pit. This reduces soil stability and increases the risk of flooding, soil instability, and unsafe working conditions. Therefore, effective groundwater management was necessary to maintain excavation safety and ensure construction could continue smoothly. The third problem was variable ground conditions and rock excavation. During excavation, the contractor encountered different types of ground, including residual soil, weather rock, and limestone. Some areas contain hard rock that required specialized excavation equipment and technique. These changing ground conditions reduce excavation efficiency and increase both construction time and operating costs. For the final problem is ground settlement affecting adjacent structures, like TRX. Deep excavation changed the surrounding conditions, the surrounding of soil conditions, which could lead to settlement around nearby buildings, roads, and underground utilities. Since several existing and historic structures were located close to the project site, continuous monitoring was required to ensure that the settlement remained within the safe engineering limits and did not affect the surrounding infrastructure. To overcome these problems, several engineering solutions were implemented throughout the stage. For the first solution is stage excavation and effective site planning. The excavation works were divided into several stages instead of excavating the entire site at once. The improved excavation stability, reduce congestion, and allow better coordination between different construction activities. Proper site planning also improve the movement of equipment and the transportation of the excavated materials. For the second solution is the installation of the diaphragm wall and groundwater level system. The diaphragm wall provides strong support for the excavation while reducing soil movement around the site. At the same time, the watering system control groundwater infiltration, creating safer and drier working conditions for excavation activities. Another important solution is the use of appropriate rock excavation techniques. Mechanical rock breakers and hydraulic excavators were used to remove hard rock safely while minimize vibration. This method was more suitable for an urban environment because it reduced the risk of affecting nearby buildings and public infrastructure. For the final solution is comprehensive instrumentation and monitoring. Various instruments, including incrometers, piezometers, and settlement markers, were installed to continuously monitor the groundwater movement, groundwater levels, and wall deflection. This allows engineers to detect any abnormal movement early and take immediate corrective action before serious problems occur. Based on this case study, several recommendations can be proposed to improve future earthwork projects. Firstly, building information modeling, which is BIM, should be used more extensively during the planning stage. BIM allows engineers and contractors to integrate geological data, excavation sequences, and underground utility information into a single digital model. This improves coordination between project teams, reduce design conflicts, and help ensure that excavation works are carried out more efficiently. Secondly, smart geotechnical monitoring system should be implemented to provide real-time monitoring of ground settlement, ground levels, and wall movement. By using IoT sensors and automated monitoring technology, engineers can quickly detect abnormal ground conditions and take immediate corrective actions before they become more serious. In addition, advanced site investigations and 3D ground modeling should be carried out before the excavation begins. These technologies provide a more accurate understanding of the subsurface conditions, allowing engineers to select suitable excavation method and reduce the risk of the unexpected geological issues during the construction. For the last recommendation is sustainable earthwork practice. It should be encouraged by reusing suitable excavated material, reducing construction waste, and using full efficient equipment. The practice not only minimize environmental impact, but also improve cost efficiency and support more sustainable construction in the future projects. Next, we will move to the last part, which is comparison between the two case studies, which is Tun Razak Exchange and Merdeka 118. For the project type, TRX is International Financial District. Merdeka 118, Supertall Mixed Use Development. For the location for TRX is at Jalan Tun Razak, Kuala Lumpur. Meanwhile, the Merdeka 118 at Jalan Hang Jebat, Kuala Lumpur. For the ground condition, for TRX is Canny Hill Formation with residual soil and weather rock, while the Merdeka 118 limestone formation with karst features. For the main challenges is deep basement excavation and groundwater control for TRX, which is for the Merdeka 118 is high structural load and deep foundation construction. Foundation system for TRX is diaphragm wall and dewatering system. Meanwhile, for the Merdeka 118 is large diameter port pipe and deep foundation system. Next, for the monitoring method, for the TRX is settlement and groundwater monitoring. Merdeka 118 is structural and foundation monitoring. Next, for the safety measures, TRX is excavation inspection and geotechnical monitoring. Meanwhile, the Merdeka 118 is structural monitoring and safety management. For the environment measure, groundwater management and traffic control for the TRX. For the Merdeka 118 is noise, vibration, and heritage protection. Lastly, for the main engineering focus, for the TRX, excavation stability and groundwater management. Lastly, for the Merdeka 118, foundation strength and structural stability.
In conclusion, earthworks are a critical stage in construction that ensure foundation stability, safety, and long-term structural performance. The case studies of TRX and Merdeka 118 demonstrate that although both projects have different construction challenges, they successfully apply proper site investigation, excavation methods, groundwater management, returning system, and continuous monitoring to achieve safe, efficient, and sustainable earthwork operations. Overall, these case studies highlight the importance of proper engineering design, construction planning, and quality control in ensuring the success of a modern earthwork project. That's all from us. Thank you for watching.